Jenna. I'm happy to be here too.
Yeah, the floor is yours. Let's start.
Okay, thank you. So, like she said, I'm Ibulin Gong. I'm a second year PhD student at the University of Vermont, and today I'm going to be giving a talk about privacy preserving machine learning. My hope is that at the end of this talk, you should understand why data privacy is important in machine learning and how it can be applied. So let's begin. What exactly is data privacy? Data privacy is an area of data protection that is concerned with the proper handling of sensitive data. So this can include personal data, other confidential data like health data, financial data, intellectual property data. And to be more specific, it gives an individual control over how their data is collected, how it is processed, stored, and shared. So it is actually a human right. It gives the right to know what information is being collected, why it is being collected, and how it's going to be used. This means that information should only be shared with those who have a need to know and who have agreed to keep the information confidential. But why should we care about data privacy in machine learning? So in privacy research, we are interested in how we can use data to solve problems while protecting the privacy of individuals. So these days, more and more companies are collecting massive amounts of data, which they use to improve their products and services. And it's great because it improves the user experience and it helps businesses to make informed decisions. But the data that they collect is sensitive information about individuals, which can be leaked. And also, companies that make these decisions have data analysts and database administrators who have access to this sensitive information. So the example on this screen is an autocomplete machine learning model, which predicts the next word. And you can see that it leaks information about the location of a meeting of revolutionaries. So the police could get this information and arrest these people. So which is like a serious privacy violation. And another reason why we should care is that AI models have been shown to memorize data. So some researchers demonstrated this in 2021, where they were able to extract personal information like people's names, phone numbers, emails from training data of GPT-2. GPT-2, which is like the predecessor of GPT-3, and that's what ChatGPT, which became so popular, is built on. And it was shown that it memorizes training data. Another example of memorization can be seen on Google Translate, where the word dog was typed several times, and it led to the model spitting out this information, which was part of the training data. And this could have easily been sensitive information. And this problem is not only limited to natural language NLP models or large language models. Only a few weeks ago, the same researchers who extracted the data from GPT-2 were able to reconstruct people's pictures on popular diffusion models like Stable Diffusion, DALL-E, Imagine, which have been trained on tons of images that include copyrighted images, trademarked images, private and sensitive images. And this work and a few others have been able to show that image models can also memorize individual training examples, which can lead to privacy violations. So one of the goals of data privacy techniques is to help prevent this memorization. Another place where data privacy can be useful is in control. So it prevents our data from being used against us. So there's a documentary on Netflix called The Social Dilemma, where former engineers and researchers in big tech companies are talking about the dangers of social media. One of the things they point out is how these companies make their money from user addiction. So they want you to stay on their app for as long as possible, which increases engagement, and more engagement means more money, more ads, which means more money. So they can do targeted advertising based on your behavior. And I don't know if some of you have noticed this, but it has definitely happened to me and a couple of my friends where we have a conversation about something like sneakers. And then when I go to Instagram or Facebook, I'm bombarded by sneaker ads. So that's one concern that data privacy is trying to address. And it can also be used to prevent sensitive data from being used for tasks which the user hasn't explicitly given consent for. So for example, Amazon employees were listening to conversations of Alexa users. So, which is a serious privacy violation because you don't want to have personal conversations in your home, and some Amazon employees are listening to it. So this is where contextual integrity comes in. Contextual integrity means that the information should only be shared with people who need to know information and in ways that are appropriate for for a particular situation. And finally, we should care because we solve some of the most important problems of the world if we can access some data. So medical problems like cancer, depression, they cannot easily be solved today because the data is too personal to access. So deep learning relies on data and tons of data and most of this data is distributed across countries, organizations, and some of them are too expensive, they're too personal for legal reasons or even because of competition. We cannot access the data. So, but data privacy can give us this superpower of accessing data that we cannot see or that we don't have access to. So for me, this is like one of the most magical and interesting aspects of data privacy, that it can let you access data that you cannot see or you don't have access to. And just some questions that privacy research is places emphasis on, is trying to answer is this kind of like a summary. So we have input privacy. How can we prevent a malicious act of, how can we guarantee that users' input data cannot be observed by other parties, including those who build the models? How can we guarantee that the output of how can we prevent a malicious actor from reverse engineering the training data, like in the example of the computer vision models where they memorize people's training data? How can we guarantee that the model cannot be stolen by a malicious party? And how do we prevent misuse or control? So can we prevent our data from being used against us? Can we solve problems or train a model on data that we cannot see? So that's the big picture. So we want to find techniques that can achieve input privacy, output privacy, prevent control or misuse, and perform remote data science. Before we look at some privacy techniques that can help us accomplish these goals. Let me make it clear that data privacy is not data security. Security policies control who can access the data, while privacy controls what you can do with the data. So security ensures that only authorized parties can access and use data. So it's kind of protecting the data itself, while privacy is controlling how the data is collected, how it is processed, how it is stored, how it is shared. So they are both important for protecting personal information, but they address different aspects of the same issue. Okay. So we are going to look at 4 privacy techniques: differential privacy, federated learning, secure multi-party computation, and homomorphic encryption. To understand how these techniques work, we'll apply them in a particular context, and our use case here is going to be in finance. So where a bank wants to use machine learning algorithms to analyze customer financial data to improve loan approval processes. So let's begin with differential privacy. So differential privacy provides formal guarantees that the output of a model does not reveal too much information about any individual that is present in the data set. So the goal of the differential privacy is to learn as much as possible about a population while learning as little as possible about any individual in that population. So with differential privacy, we can learn, for example, that smoking causes cancer, but we don't know whether John, who is in the data set, has cancer or not. Or if you looking at our use case, we can learn that certain financial characteristics are indicative of a high credit risk, but we cannot learn whether John, who is in the data set, has a high credit risk or not. So it works by, and how does it work? It works by adding random noise to the data. So if you just add noise to your data or add noise to the process, you can achieve differential privacy. But the challenge here is how much noise should you add? Because the more noise you add, the less useful your data is. You can see from this image here you have no privacy at all because when you add noise, because there's no noise. But as you add noise, the image becomes less visible and less useful. So we are trying to find a sweet spot, like somewhere here where we can get some utility, but also get some privacy. An important parameter in differential privacy is called epsilon, or the privacy budget, which determines the amount of information, it determines the amount of information that can be revealed about an individual data point. So small values of epsilon lead to stronger privacy guarantees, protections, while larger values of epsilon lead to weaker protection. So you can see if you have a small value of epsilon, it means we're adding more noise and we get more privacy, but the accuracy is very low. And if the larger the epsilon gets, we get less noise, less privacy, but more utility or more accuracy. In differentially private machine learning, noise can be added at different levels. So it could be added to the input data. It could be added at intermediate values when you're training your model, like to the gradients of your model while training. Noise can be added to the loss function and to the output of the machine learning model. And the most popular method is called differentially private stochastic gradient descent, which is an algorithm perturbation method, which we'll look at in a moment. But in regular machine learning, when you have a data set, you get a mini batch, compute the gradient on that mini batch, update the model parameters in the opposite direction to improve your model, and then you do this over and over until your machine learning model learns. With differentially private stochastic gradient descent, you get your mini batch, compute the gradients of each example in your mini batch. You clip the gradient to bound its sensitivity. You compute the average of these gradients. Then you add noise to that average, and then you continue training your model like the same way you train like a standard machine learning model. So with this small change, we're able to get privacy in our machine learning models. But we don't get this privacy for free. We have to pay a cost in accuracy, as you can see in these graphs, like on these popular models like MNIST, the MNIST dataset, FMNIST, the baseline is like 99% and 89% and 76% when you train your machine learning model without any privacy, so without any noise added. But if you add noise to them, you see that you get an accuracy of like 96%, so instead of 99%. So you kind of lose some utility, but you also get privacy. So with differential privacy, it requires a careful balance between the privacy guarantees and the quality of the result. And this is kind of an active area of research about how to get the most privacy and the most utility at the same time. So looking at the big picture, where differential privacy fits in the big picture, it can be used for input privacy. It can prevent control and misuse. And no, it cannot be used for remote data science. No, not really. But let's look at federated learning. Okay, federated learning is a type of distributed machine learning approach where the model can be trained on decentralized data. So in traditional machine learning, the data is collected from different devices and stored in a central server. And then the data scientist trains their machine learning model on this central data set. So here, users have to trust the central data set with sensitive information. Okay, but in federated learning, the data stays on the user's device, and the data scientist sends the model to the user's device where it is trained. The trained model is then uploaded to a central server, and the results are aggregated and sent back to the user's device. So the process continues until the machine learning model achieves the required accuracy. So basically, in federated learning, we are bringing the model to the data instead of the data to the model. And this does not have to happen only with user devices. It can be extended to organizations like schools and hospitals. So if we go to a bank, so our bank use case, a bank could use federated learning to train a loan approval model in collaboration with other financial institutions. Each institution would keep its data on its own servers and only send model updates to the bank. The bank would then aggregate these updates to produce a shared model. So federated learning can enable collaboration in a privacy-preserving way, making it possible to train models on a larger and a more diverse range of data. So how does federated learning fit into the big picture? It can prevent control and misuse, and it enables remote data science. But the green check mark with the cross on shows that federated learning can help with input privacy and model privacy, but only to a certain extent. It doesn't completely solve the problem. The next technique we'll look at is secure multi-party computation, or MPC for short. MPC is a privacy-preserving technique that allows multiple parties to compute on data without revealing the data to each other. So say, for example, we have these 4 people who want to compute the average of their salaries without disclosing the actual salaries to each other. So an average salary is computed by computing the sum of the 4 values and then dividing it by 4. And then we get this value, 3,675. And that is the average salary. So this problem can be solved using something called additive secret sharing, which can be done by each person encrypting their salaries into something we call shares So each person divides, like this person takes his salary is 5,000 and divides this salary into 4 different shares. These shares are random numbers and they should all add up to 5,000. So everyone does that. Everyone takes their salary and divides it into these 4 shares. And then the random shares are then, after doing that, the random shares can be distributed among the different parties. So this person gets 1 share from each person. Everybody gets 1 share from the other person, and you can get this value. When everyone adds up the shares that they get, they have a new sum, which is like, you can see that the sum is completely useless because it does not reveal anything about the other person's salary. So these are the sum that everyone gets. Now, these parties can combine this total sum, these total shares, and learn that the sum of their shares is 14,700. And if you divide this 14,700 by 4, you get 3,675, which is the original average salary. So the amazing thing is that we have been able to use this additive secret sharing to compute this average salary without anyone knowing the actual salary of the other person, or without sharing the salaries to a third party like a server to add the salaries together. So this is basically it's kind of a summary of how MPC works. In our bank example, a group of banks could use MPC to share customer financial data with each other to determine the credit risk of potential borrowers. And this can allow the banks to make more informed learning decisions without revealing the confidential information about their customers. And this is simple MPC protocol, and there are more MPC protocols, but this is basically how they work. And MPC provides input privacy, it provides some model privacy, prevents control and misuse, and enables remote data science because it allows different people, like the different banks, to collaborate, or different hospitals can collaborate together without actually revealing their data. Okay. The final one technique we're going to look at is called homomorphic encryption. And homomorphic encryption allows computation to be performed on encrypted data. So, for example, if you have 2 values, you encrypt like 5,000 and 3,500. You can encrypt these 2 values and then compute the sum of the encrypted values together. When you decrypt these sums, when you decrypt the sum, you can get the final sum, which is 8,500. So it's like adding 5,000 and 3,500 together, but the computation does not know what the original value is. So we've been able to perform an operation on these 2 numbers without actually revealing what those numbers are. We just got the sum, and you don't know what are the values that made up this sum. And that's basically a very small basic description of how homomorphic encryption works. In our finance example, the bank could use homomorphic encryption to perform machine learning computations on encrypted customer financial data, and the encrypted data will never be decrypted, ensuring that it remains confidential. And if we look at this in our big picture, you can see that homomorphic encryption, it works similarly to MPC. It provides similar guarantees. So you can either use, most of the time, you can choose to use MPC or homomorphic encryption depending on what you're trying to accomplish. And this final picture shows that there is no privacy technique that's a silver bullet, because different privacy techniques solve different problems. To obtain higher degrees of privacy, it may be necessary for us to combine several privacy preserving machine learning techniques to accomplish a particular goal. And yeah, so even though these privacy techniques we have seen today have already shown promising results, there is still much work to be done to further develop and improve them. So their efficiency, scalability, their application in real-world scenarios require further research. And if you want to learn more or contribute to this field, you can check out organizations like OpenMind, OpenDP, Tumult, and some of them are even provide libraries like TensorFlow, like in TensorFlow Federated, or PyTorch, Opicus, which works with PyTorch, which allows data scientists to incorporate privacy into their workflow. Yeah, I hope you've been able to learn something from today's talk, and thank you for listening.
Thank you, Ivy.
I'll be happy to answer any questions.
Yes, there are a couple of questions Sorry, but first I want to read a comment that someone sent.
Yeah.
So Andres said, this session is really amazing. I would like to watch it again. How can we access the recording? So as I've been telling you before in other talks, this one is being recorded and Ivy agreed to record it and it's going to be published in Factor's YouTube channel. So you can rewatch it again.
Mm-hmm.
So, but yes, there are other questions in the chat.
Okay.
I think this question came when you were explaining about differential privacy. Yeah, the first method that you were talking about. Carlos asks, does not this change or affect the performance of the models?
Yes. Yeah. Okay. Good. Yeah, it actually does affect the performance of the model. If I go to, let me go to the slide. So if you notice, this is like the MNIST data set, the FMNIST data set. This baseline is 99%. So this is like training the model without any noise, any privacy. But when you add noise, the privacy reduces to like 95 point something percent, as you can see here, or 96%. And it affects all the different models. So yes, it's adding noise affects the privacy of the model, and it's an open question that we are trying to solve, and researchers are trying to improve. And yeah, so we cannot get privacy for free.
Yeah, as you were mentioning at the beginning of the talk, like if we are going to add some noise, that we're going to need to sacrifice some efficiencies or accuracy, but the idea is to find that balance, right?
Exactly. Yeah.
Yeah. There is another question. You mentioned multiple places where you can apply differential privacy on a training procedure. Yes. Is there any preference or advantage of one over the other? I think they're talking about the methods.
Yeah. Okay. Yeah. So we have these different places where you can add noise to the differential privacy model, and yeah, the best method, like the state of the art method, is the one I introduced. The one called differentially private stochastic gradient descent. This method, and where in this method you're adding noise to the gradients. So it has been shown that most of these other methods, adding noise to like the input or the output, affects the privacy very badly. So far, this is the best technique. But it's also an open area of research. So tomorrow, someone may come up with a new way of adding noise adding noise to the machine learning process that is much better. Yeah. But the current state of the art is the GPSGT.
Mm-hmm.
That's your question. Yeah.
Well, let's ask the person who asked. Does that answer the question? You can answer in the chat.
Mm-hmm.
Okay, I hope it does. So there's another question from Andres. There is something I want to understand better. How can internal parameters of the model actually affect the privacy? You mentioned this when you were talking about the gradients.
Okay. Yes. So depending on the amount of noise, so depending on the kind of model you're doing, right? It has been shown that the bigger the model, the lower privacy you get. So I think on this slide we have something like that. So larger models have bigger accuracy penalty. So if you have very large models, most of the time your accuracy is going to be very low, which is surprising. But in most cases, that's what happens. So with smaller models, like if you have a smaller architecture, there's a higher guarantee of you having a better privacy after adding noise. But recently, some researchers published a paper where in natural language, if you're using fine-tuning in natural language processing models, like large language models, the opposite happens. So with the larger the model, the better privacy and accuracy you get. But that's like a very specific case. Most of the time, smaller models actually produce better results.
Do you know? No, I'm sorry. Go ahead.
Yeah, smaller architectures produce better results. So I hope that answers the question.
Yes, Andres says yes. Thank you for your answer. Do you know if there is already an effort to apply any of these methods for privacy in large popular models like DALL-E or ChatGPT?
Yeah, I don't think they've applied them to these like popular models yet, because it affects their privacy very badly. But many companies like Google, so in this slide, I think in the final slide, these companies here, these organizations, Google, IBM, Facebook, the US Census Bureau, they have all deployed private models like in their systems. So, for example, even Apple is not here, but Apple has, the US Census used privacy in the last census in 2020. They used differential privacy to be able to analyze and collect information. And then Google recently they deployed a model that uses differential privacy and federated learning to improve like messaging, the chat on Android phones. But I'm not sure how much how far the deployment has gone, but they had a blog post that said they're doing that. So many more companies are trying to implement this into their models. Yeah. It's also possible that ChatGPT, OpenAI may use privacy because in order to prevent like ChatGPT from memorizing training data. So it's possible they may implement this, yeah. So there.
So there's a question from Alejandro. Homomorphic encryption used to be computationally expensive a few years ago, increasing inference and training times by orders of magnitude. Has that changed recently?
Yeah, not really. So homomorphic encryption is still very slow. So there are different types of homomorphic encryption, which I did not talk about here, but you have like the partial homomorphic encryption, and then you have fully homomorphic encryption. There have been some improvements from a couple of years ago, but it's still very slow. So yeah, it's still an open area of research. There are so many things that are still like open areas of research, open questions that people are working on. And hopefully in a couple of years, homomorphic encryption will be faster. Yeah.
Let's hope so.
Yeah.
And faster and more accessible.
Yes.
Not so expensive.
Yes.
Alejandro is asking, is there any privacy advantage of using adversarial examples during training?
Yes. So it depends. Different methods, there are different machine learning models, and some that people have proposed different privacy techniques, and some privacy techniques actually use adversarial examples. But most of the time, adversarial examples are used to break the privacy techniques. So you can propose. I can propose a privacy technique, and then someone uses an adversarial example to show that what I'm proposing does not work. So most of the time, adversarial examples are being used as applied as a way to attack the proposed privacy methods. Yeah. So, yeah, I don't know if that answers the question.
Let's ask Alejandro. Alejandro, can you put in the chat if that answered your question, please? I believe it was Alejandro. Okay. Someone is actually requesting their hand. Daniel Gutierrez, do you want to talk? I can allow you to talk. I'm going to take that as a yes. Let us know what your question, Daniel. Okay, maybe he got confused with the controls. There's another question. What other methods, apart from adding noise, are being used to preserve machine learning in ML models?
Okay, so adding noise is only done with differential privacy. These other techniques, and these are just a few. These are like the most popular techniques are used to privacy preserving techniques. So like federated learning and MPC, which we talked about, and homomorphic encryption. You also have other things like secure enclaves, and yeah, there are like a whole lot of methods that people are proposing to be able to secure privacy in machine learning.
Okay. I think that covers all the questions that I see on the chat.
Okay.
Yes, I think I covered them all. If there are any more questions, it was so good to have you here, Ivy. I think that you did a great job explaining everything so very clear. So thank you so much. It is always amazing to learn about how privacy is super important. How should we care about that? How should we learn why we should care about that? How should we be responsible whenever we are creating a model and thinking on this? So thank you so much for being here.
Yeah, it was my pleasure. And yeah, very good questions from everyone. Thank you.